When dealing with single-phase loads at 208 volts or 240 volts, the voltage drop calculation generally follows this formula: voltage drop equals load current multiplied by circuit length multiplied by resistance per unit length. Let's break down each component. Load current represents the amount of current, measured in amps, that the load draws. Circuit length refers to the total length of the wire run, usually measured in feet. Resistance per unit length signifies the wire's resistance per unit length, typically expressed in ohms per foot. For three-phase loads, the voltage drop calculation has a slight variation because of the presence of multiple phases. To find the voltage drop, perform the same formula: voltage drop equals load current multiplied by circuit length multiplied by resistance per unit length for each phase individually. The total voltage drop is calculated by adding the voltage drops across all three phases. Determining the resistance per unit length is crucial. You can find this information in wire tables or the National Electrical Code, specifically Table 8. Make sure to use the correct value that corresponds to the wire size and the material it's made of. The National Electrical Code Table 9 along with Note 2 offers a simplified way to calculate voltage drop for balanced three-phase loads. This method uses a multiplier factor that accounts for the phase relationship of the load. Now let's talk about the overall approach. Firstly, you need to determine the load current. Calculate how much current the load draws, considering its power factor and power consumption. Secondly, calculate the circuit length. Measure the total distance from the power source all the way to the load. Thirdly, determine the resistance per unit length. You can find this resistance value from wire tables or the National Electrical Code. Fourthly, calculate the voltage drop. Use the right formula based on whether you're dealing with single-phase or three-phase loads. Fifthly, select the appropriate wire size. Choose a wire size that ensures an acceptable voltage drop. Always remember to refer to the local electrical code and follow the specific requirements for your installation. To elaborate, let's consider a practical example for a single-phase 240-volt load. Imagine a motor drawing 20 amps located 100 feet away from the electrical panel. We're using 12 American wire gauge copper wire, which has a resistance of approximately 2.0 ohms per 1000 feet, or 0.2 ohms per foot. Using the formula, voltage drop equals load current multiplied by circuit length multiplied by resistance per unit length, the calculation would be voltage drop equals 20 amps multiplied by 100 feet multiplied by 0.2 ohms per foot, which equals 4 volts. This means there's a 4 volt drop along the 100-foot wire run. To put this in perspective, the percentage voltage drop is calculated as voltage drop divided by source voltage multiplied by 100. In this case, it's 4 volts divided by 240 volts multiplied by 100, which equals 1.67%. In many applications, a voltage drop of less than 5% is considered acceptable, so this would likely be within the acceptable range. Now let's consider a three-phase 480-volt load, such as an air conditioning unit. Suppose this unit draws 15 amps per phase and is located 150 feet from the electrical panel. We're using 14 American wire gauge aluminum wire, which has a resistance of approximately 3.1 ohms per 1000 feet, or 0.31 ohms per foot. The voltage drop for one phase would be voltage drop equals 15 amps multiplied by 150 feet multiplied by 0.31 ohms per foot, which equals 0.6975 volts. Since this is a three-phase system, the total voltage drop is not simply 3 times this value. Instead, the voltage drop between any two phases is square root of 3 multiplied by the phase voltage drop. To find the percentage voltage drop in a three-phase system, you first calculate the line to neutral voltage drop, then divide by the source line to neutral voltage, and multiply by 100. The line to neutral voltage for a 480 volt system is 480 volts divided by square root of 3, which is approximately 277 volts. The percentage voltage drop would be 0.6975 volts divided by 277 volts multiplied by 100, which is approximately 0.25%. Again, this is likely within an acceptable range. Remember that these are simplified examples. In real-world scenarios, other factors such as temperature correction, conduit fill, and bundling of conductors can affect the resistance and reactance of the wires, influencing the voltage drop. The National Electrical Code provides guidance on these factors, and it's essential to consult the code and engineering references for accurate calculations. Now let's delve a bit deeper into the factors that influence voltage drop and how to mitigate them. Firstly, the length of the circuit has a direct impact on voltage drop. Longer circuits will naturally experience a greater voltage drop due to the increased resistance of the wire. To counteract this, consider using larger conductor sizes for longer runs to reduce resistance. Secondly, the load current is another critical factor. Higher load currents result in greater voltage drops. If the load current is expected to be high, it may be necessary to use larger conductors or run multiple parallel conductors to distribute the current and reduce voltage drop. Thirdly, the conductor material plays a significant role. Copper and aluminum are the most common conductor materials, with copper generally having lower resistance than aluminum. However, aluminum is lighter and less expensive, making it suitable for certain applications. When using aluminum conductors, it's essential to choose a larger size than you would for copper to achieve the same level of voltage drop performance. Fourthly, temperature affects the resistance of conductors. As the temperature of a conductor increases, its resistance also increases, leading to greater voltage drop. This is particularly important in high-temperature environments or when conductors are bundled together, which can trap heat. To address this, direct the ampacity of the conductors according to the National Electrical Code guidelines to account for the increased temperature. Fifthly, reactance, which is the opposition to alternating current flow, can also contribute to voltage drop, especially in non-AC circuits. Reactance is caused by the inductance and capacitance of the conductors. To minimize reactance, use conductors with lower inductance and consider using conduit materials that minimize eddy currents. Sixthly, power factor affects voltage drop in AC circuits. Power factor is the ratio of real power to apparent power, and it indicates how effectively electrical power is being used. A low power factor can result in increased current flow and greater voltage drop. To improve power factor, consider using power factor correction capacitors, which reduce the reactive component of the current. Seventhly, the number of conductors in a conduit can influence voltage drop. When multiple current-carrying conductors are bundled together in a conduit, they can generate heat, increasing the temperature and resistance of the conductors. To mitigate this, follow the National Electrical Code guidelines for conduit fill and dirting of conductors. Eighthly, the type of load can also affect voltage drop. Resistive loads, such as heaters and incandescent lamps, have a constant current draw, while inductive loads, such as motors and transformers, have a varying current draw that can cause voltage fluctuations. For inductive loads, it may be necessary to use larger conductors or voltage regulators to maintain stable voltage levels. Ninthly, the source impedance of the power supply can contribute to voltage drop. A high source impedance can cause voltage to sag under heavy load conditions. To address this, consider using a dedicated transformer or upgrading the power supply to reduce the source impedance. Tenthly, grounding and bonding practices can also influence voltage drop. Proper grounding and bonding can minimize voltage fluctuations and ensure that equipment operates safely and reliably. Follow the National Electrical Code guidelines for grounding and bonding to ensure that the electrical system is properly protected. When performing voltage drop calculations, it's essential to use accurate data and consider all relevant factors. The National Electrical Code provides tables and guidelines for conductor resistance, ampacity, and dirting factors. Engineering handbooks and software tools can also assist with voltage drop calculations. To summarize, voltage drop is an important consideration in electrical system design and installation. By understanding the factors that influence voltage drop and taking appropriate measures to mitigate it, you can ensure that electrical equipment operates safely and efficiently. Always consult the National Electrical Code and engineering references for accurate calculations and guidance. In addition to the points already discussed, let's consider some best practices for minimizing voltage drop in electrical installations. Firstly, plan ahead. Before starting any electrical installation, carefully plan the layout of the circuits and determine the expected load currents and circuit lengths. This will help you select the appropriate conductor sizes and minimize voltage drop. Secondly, use the shortest possible wire runs. Wherever possible, keep wire runs as short as possible to minimize resistance and voltage drop. Avoid unnecessary bends and loops in the wiring. Thirdly, use high-quality conductors. Choose conductors that meet or exceed the requirements of the National Electrical Code. High-quality conductors will have lower resistance and better insulation, which can help minimize voltage drop and prevent electrical hazards. Fourthly, use proper termination techniques. Ensure that all wire terminations are properly made and tightened. Loose or corroded terminations can increase resistance and voltage drop. Use appropriate connectors and tools for the type of wire and equipment being used. Fifthly, use separate neutral and ground conductors. In AC circuits, use separate neutral and ground conductors to minimize the flow of current through the grounding system. This can help reduce voltage drop and prevent ground loops. Sixthly, use surge protection devices. Install surge protection devices at the service entrance and at sensitive equipment to protect against voltage surges and spikes. Surge protection devices can help maintain stable voltage levels and prevent damage to equipment. Seventhly, perform regular maintenance. Inspect electrical systems regularly for signs of wear, corrosion, or damage. Repair or replace any damaged components to prevent voltage drop and electrical hazards. Eighthly, consider using voltage regulators. In areas with fluctuating voltage levels, consider using voltage regulators to maintain stable voltage levels and prevent equipment malfunctions. Ninthly, use energy-efficient equipment. Choose energy-efficient equipment that draws less current and reduces the overall load on the electrical system. This can help minimize voltage drop and save energy. Tenthly, consult with a qualified electrician. If you are unsure about any aspect of electrical system design or installation, consult with a qualified electrician. A qualified electrician can help you select the appropriate conductor sizes, perform voltage drop calculations, and ensure that the electrical system meets all applicable codes and standards. To further expand on these points, let's consider some specific scenarios and how to address them. Firstly, in long branch circuits, such as those used for lighting or receptacles, voltage drop can be a significant issue. To mitigate this, consider using larger conductor sizes or running multiple parallel conductors to distribute the current. You can also use voltage drop calculators to determine the appropriate conductor size for the length of the circuit and the expected load current. Secondly, in motor circuits, voltage drop can cause motors to overheat and fail prematurely. To prevent this, select conductors that are sized to handle the motor's starting current, which can be several times higher than the running current. You can also use motor starting devices, such as reduced voltage starters, to limit the starting current and reduce voltage drop. Thirdly, in panel board feeders, voltage drop can affect the performance of all the circuits fed by the panel board. To minimize voltage drop in panel board feeders, use larger conductors and keep the feeder length as short as possible. You can also use step-down transformers to reduce the voltage at the panel board and compensate for voltage drop. Fourthly, in service entrance conductors, voltage drop could affect the entire electrical system. To minimize voltage drop in service entrance conductors, use the largest conductors allowed by the National Electrical Code and keep the service entrance as close as possible to the utility transformer. You can also use automatic voltage regulators to maintain stable voltage levels at the service entrance. Fifthly, in emergency power systems, voltage drop can compromise the reliability of the system. To minimize voltage drop in emergency power systems, use dedicated circuits for critical loads and size the conductors to handle the maximum expected load current. You can also use uninterruptible power supplies to provide backup power and maintain stable voltage levels during power outages. Sixthly, in renewable energy systems, such as solar and wind power systems, voltage drop can reduce the efficiency of the system. To minimize voltage drop in renewable energy systems, use dedicated circuits for the renewable energy sources and size the conductors to handle the maximum expected current. You can also use DC-DC converters to boost the voltage and compensate for voltage drop. Seventhly, in data centers, voltage drop can affect the performance of sensitive electronic equipment. To minimize voltage drop in data centers, use dedicated circuits for critical equipment and size the conductors to handle the maximum expected load current. You can also use power distribution units with voltage regulation to maintain stable voltage levels. Eighthly, in industrial facilities, voltage drop can cause production equipment to malfunction and shut down. To minimize voltage drop in industrial facilities, use dedicated circuits for critical equipment and size the conductors to handle the maximum expected load current. You can also use variable frequency drives to control the speed of motors and reduce the overall load on the electrical system. Ninthly, in commercial buildings, voltage drop can affect the comfort and productivity of occupants. To minimize voltage drop in commercial buildings, use dedicated circuits for lighting and HVAC equipment and size the conductors to handle the maximum expected load current. You can also use energy management systems to optimize the use of electricity and reduce voltage drop. Tenthly, in residential buildings, voltage drop can cause lights to dim and appliances to operate inefficiently. To minimize voltage drop in residential buildings, use dedicated circuits for major appliances and size the conductors to handle the maximum expected load current. You can also use arc fault circuit interrupters to protect against electrical fires caused by voltage drop. In conclusion, voltage drop is a complex issue that can affect the performance and safety of electrical systems. By understanding the factors that influence voltage drop and following best practices for minimizing it, you can ensure that electrical equipment operates efficiently and reliably. Always consult the National Electrical Code and engineering references for accurate calculations and guidance, and consult with a qualified electrician if you have any questions or concerns. Furthermore, it's crucial to stay updated with the latest industry standards and technological advancements in electrical system design and installation. For instance, the National Electrical Code is revised every 3 years to incorporate new technologies and address emerging safety concerns. Familiarizing yourself with these updates will help you stay current with best practices and ensure that your electrical installations meet the latest requirements. Additionally, advancements in conductor materials, such as high-temperature superconductors, are constantly being developed. These materials offer the potential to significantly reduce resistance and voltage drop, but they may also require specialized installation techniques and equipment. Staying informed about these emerging technologies will allow you to take advantage of their benefits and improve the performance of your electrical systems. Another important aspect to consider is the impact of harmonics on voltage drop. Harmonics are distortions in the AC waveform that can be caused by nonlinear loads, such as electronic devices and adjustable speed drives. Harmonics can increase the current flowing through the electrical system, leading to greater voltage drop and potential overheating of conductors and equipment. To mitigate the effects of harmonics, consider using harmonic filters or reactors to reduce the harmonic content of the current. You can also use shielded cables and grounded enclosures to minimize the propagation of harmonics. Furthermore, it's important to conduct regular power quality audits to identify and address any harmonic issues in your electrical system. These audits can help you determine the sources of harmonics and implement appropriate mitigation strategies. In addition to harmonics, other power quality issues, such as voltage sags, swells, and transients, can also affect voltage drop and equipment performance. Voltage sags are temporary reductions in voltage, while voltage swells are temporary increases in voltage. Transients are short-duration, high-voltage spikes. These power quality disturbances can be caused by a variety of factors, such as utility switching operations, lightning strikes, and equipment malfunctions. To protect against power quality disturbances, consider using surge protection devices, uninterruptible power supplies, and voltage regulators. You can also use power quality monitoring equipment to track voltage levels and identify any potential problems. Another important consideration is the impact of distributed generation on voltage drop. Distributed generation refers to the generation of electricity at or near the point of consumption, such as solar panels on a rooftop or a backup generator at a commercial building. Distributed generation can affect voltage drop in a number of ways. For example, if the distributed generation source is located far from the load, it can increase the voltage drop on the circuit. Conversely, if the distributed generation source is located close to the load, it can reduce the voltage drop. To properly integrate distributed generation into an electrical system, it's important to conduct a thorough voltage drop analysis and ensure that the conductors are sized appropriately. You may also need to install additional protective devices to prevent overvoltage and undervoltage conditions. Finally, it's important to remember that voltage drop is just one factor to consider when designing and installing an electrical system. Other factors, such as safety, reliability, and cost, are also important. By taking a holistic approach to electrical system design and considering all relevant factors, you can ensure that your electrical systems are safe, efficient, and reliable.